Most of the time, we talk about climate as a slow, long-term trend. But every few years, something different happens. The Pacific Ocean, the largest feature on the planet, shifts its weight from one side to the other. That shift is called the ENSO, the El Niño Southern Oscillation, and it's one of the closest things Earth has to a heartbeat. Today we're going to take apart this natural phenomena and look at how changes in ocean temperatures near South America can help trigger droughts in Australia, floods in California, and weather extremes across the globe. We'll separate the myths from the mechanics, explain what ENSO can and can't do, and explore how climate change may be putting this natural cycle under added strain. Welcome to the podcast. I'm Dr. Mack, and this is the Climate Translation. To understand how the El Niño Southern Oscillation works, we need to start with how the tropical Pacific normally functions. In an average year, strong trade winds blow steadily from east to west along the equator. These winds push the warm surface water away from South America and towards Indonesia and Australia. Over time, that warm water actually piles up in the western Pacific, sometimes by more than a foot. That pile of warm water is important. Warm water heats the air above it, causing air to rise and create low pressure. Cooler water does the opposite. So as warm water builds up in the west, air rises there. It then flows eastward in the atmosphere and then sinks over the eastern Pacific, and then flows back west along the surface. That loop is called a Walker circulation. At the surface, this circulation reinforces the trade winds. And along the coast of South America, those winds pull surface water away from the shore, allowing cold, nutrient-rich water to rise up from the deep. This process, called upwelling, supports some of the most productive fisheries on Earth. Now, that's the baseline. That's normal. ENSO happens when the system gets knocked out of balance. During El Niño, the trade winds weaken, sometimes dramatically. When that happens, the warm water that's piled up in the western Pacific is no longer held in place. Gravity takes over, and that warm water sloshes back east towards South America. As it spreads out, the eastern Pacific warms. The cold upwelling shuts down, and the entire pressure pattern across the Pacific shifts. The atmosphere responds almost immediately. Rainfall patterns move east. Regions that are normally wet can dry out. Places that are dry can see flooding. And because the Pacific is so large, those changes ripple outward into weather patterns across most of the globe. Now, La Niña is the exact opposite. The trade winds just don't strengthen, they go into overdrive. Warm water is pushed even farther west. Cold upwelling in the east intensifies, and the temperature contrast across the Pacific becomes stronger than normal. That supercharged contrast locks the Walker circulation into a more intense version of its usual pattern, often bringing cooler global temperatures and a different set of climate impacts worldwide. So it's the same system, just different settings. A useful way to think about ENSO is as a giant bathtub. In a normal year, it's like your hands are pushing water towards one end. That's the trade winds doing their job. During El Niño, your hands stop pushing and the water sloshes back the other way. During La Niña, you push harder than usual, exaggerating the imbalance. The tub hasn't changed. The water hasn't changed. What's changed is the force applied to the system. And that's a key point. ENSO isn't a storm. It's not a switch that flips on and off. It's a natural oscillation, a back and forth movement that's coupled to the ocean atmospheric system. Understanding that seesaw is the key to understanding everything that follows, including why ENSO has global effects, why its impacts aren't the same everywhere, and why climate change complicates the picture without directly causing El Niño or La Niña. The El Niño Southern Oscillation has a direct impact on the ocean's food delivery service. In the eastern Pacific, especially off the coast of Peru, the normal state of the ocean is surprisingly generous. Strong trade winds push surface water away from the coast, and the cold water rises up from the deep to replace it. That rising water is packed with nutrients, things like nitrates, phosphates, and iron, eroded from rock and stored in the deep ocean. When they reach the sunlight, microscopic plants called phytoplankton explode in number. That plankton feeds anchovies. Anchovies feed larger fish. Birds, seals, and whales feed on all of it. It's one of the most productive marine ecosystems on Earth. That's the East Pacific Feast. In my oceanography classes, this is usually when a student asks, well, if the water is colder, why is it better for life? It's because cold water from the depths is old water. It's been sitting in the dark collecting nutrients for decades or even centuries. Warm water, by contrast, is often nutrient poor. It's been stripped clean by biology already. It's not the temperature that matters as much as the nutrients. During El Niño, when warm water sloshes eastward, that nutrient conveyor belt breaks down. The warm surface water thickens and acts like a lid to the ocean. The upwelling slows or shuts off entirely. The nutrients can't reach the surface sunlight. Phytoplankton production crashes, and the entire food web begins to unravel. Anchovies either migrate or die off. Seabirds abandon nesting sites or starve in some cases. Fisheries can collapse even within months. So, can't the fish just eat something else? I might be asked. Well, not easily. Marine food webs are efficient but fragile. When the base collapses, there's usually nothing to replace it very quickly. You can't really skip steps in an ecosystem. But not all marine life loses during El Niño. As warm water spreads poleward, species that prefer more tropical conditions can follow it. Fish like mahi-mahi, tuna, and even some sharks suddenly appear far outside their usual ranges. During especially strong El Niño events, you can even find some tropical fish as far north as San Francisco. Of course, this leads to another common question. Does that mean climate change is happening there? Well, not necessarily, and that's an important thing to note. ENSO doesn't create new species or new behaviors. It rearranges where existing species can survive temporarily. When conditions shift back, many of those species retreat. But there's a catch. Repeated or extreme ENSO events can stress ecosystems faster than they can recover. Coral reefs can have more bleaching events. Kelp forests can weaken. Species that rely on stable conditions struggle to rebound before the next disruption arrives. And that leads to one last important question. If this keeps happening, does temporary start to become permanent? And that question sits at the edge of modern climate science. ENSO has always been part of the Earth system, as far as we can tell. But as the background ocean warms, the impacts of each swing can become more damaging. Not because anything here is new, but because the system it's operating in is changing. The ocean doesn't respond to ENSO once, it remembers. And understanding that memory, made up of the biological, the chemical, and the physical processes, is key to understanding why ENSO matters far beyond the Pacific Ocean. So, how does a change in ocean temperature in the middle of the Pacific end up affecting rainfall in Kansas, snowfall in California, or droughts in Australia? The answer starts with the jet stream. High above our head, the jet stream is a concentrated corridor of air that flows from the west to the east. It helps steer storms, control temperature contrast, and decide where rain and snow tend to fall. And the jet stream responds to where heat is released in the atmosphere. And that's where ENSO comes in. Think of the jet stream like a fast-moving river. Under normal conditions, it follows a familiar path. But ENSO is like dropping a massive boulder into that river. The atmosphere doesn't ignore it, it has to flow around it. It creates bends and waves and ripples that travel far downstream. During El Niño, warm water spreads east across the Pacific. The warm water heats the air above it, causing more air to rise in places where it normally doesn't. That rising air changes pressure patterns and pushes that fast-moving jet stream into a new configuration. During La Niña, the opposite happens. Heat stays farther west, and the jet stream responds in a different way. That process is called teleconnection. It's a fancy word for something that happens here that affects the weather far away. So, why doesn't this just stay over the ocean or around the ocean area? It's because the atmosphere is fluid and connected. We live on a planet where everything's connected. Once you change where the large amounts of heat enter this system, the entire circulation across the entire globe adjusts. In the United States, El Niño often shifts the jet stream southward. That makes the southern U.S. cooler and wetter, especially in winter, while the northern U.S. can end up warmer and drier than average. California is more likely to see heavy rain events, though not every El Niño guarantees them. Meanwhile, in parts of Southeast Asia and Australia, El Niño can suppress rainfall, increasing the risk of drought, wildfires, and crop stress. La Niña tends to flip many of those patterns, increasing the rainfall in the western Pacific and shifting storm tracks northward in North America. So, does El Niño cause the storms? No. ENSO doesn't create individual storms. It changes the background conditions that storms move through and either grow them or suppress them. It's where the loaded dice analogy happens. ENSO doesn't roll the dice for the atmosphere, it loads them. During El Niño and La Niña, certain outcomes become more likely. Nothing is guaranteed, though. You can still have a quiet El Niño winter or an intense La Niña season with few extremes in a given location. When it comes right down to it, climate is complicated. It's about probability, not certainty. One of the biggest misconceptions is that ENSO can explain a lot of things. Not every drought, flood, or heat wave can be blamed on La Niña or El Niño. Weather is influenced by overlapping systems, from Arctic oscillations to local sea surface temperatures to random variability. Even land cover differences can affect the weather. ENSO is powerful because it tilts the odds across large regions, though, not because it controls the outcome. And that's why ENSO is important for seasonal forecasting. It doesn't tell us exactly what will happen, but it tells us in probabilistic terms what's more likely. Understanding that difference helps prevent both overhype and misplaced blame. So, if ENSO has always been part of the Earth's system, as far as we can tell, What happens when the background climate it's operating in begins to change? Yes, ENSO has been part of the Earth's climate system for a very long time. It's a natural oscillation driven by ocean heat, winds, and pressure differences across the Pacific Ocean. Climate change didn't create it, but human-induced climate change does change the conditions ENSO operates in. Over the last several years, new research has begun to converge on a worrying problem. Studies published in 2025 and 2026 suggest the Pacific may be shifting towards what scientists sometimes call climate whiplash, larger, faster swings between very strong El Niño and very strong La Niña events. It's important to point out that not every study agrees on the details, but they all point in the same general direction. And the reason comes back to something we've already talked about, that stored heat. The oceans absorb more than 90% of the excess heat trapped by the greenhouse gases. We are an ocean world, after all. That means ENSO is now operating on top of a much warmer background than it did just even a few decades ago. Think of it this way: if ENSO is a seesaw, climate change is raising the floor underneath that middle part that holds the plank, which allows both sides to rise and lower more. So when an El Niño begins today, it's starting from a higher temperature baseline. The warm water that sloshes east isn't just warmer relative to normal, it's warmer in absolute terms. That means a moderate El Niño can produce impacts that resemble a strong El Niño from 40 years ago. It's not because ENSO itself has changed category, but because the system is interacting with already hotter conditions. So, does that mean every El Niño will be extreme now? Absolutely not. ENSO is variable. Some events will still be weak. Some years will be quiet. The cycle hasn't become a metronome, but the risks are growing. When ENSO does swing strongly, it now has more energy to work with, more ocean heat to release into the atmosphere, more moisture to fuel storms, and higher background temperatures to amplify heat waves and droughts. Another key insight from research is that stronger swings can arrive closer together. In the past, a strong El Niño might be followed by several calmer years. But as the ocean stores more heat, the system can be primed to rebound sharply, flipping from El Niño to La Niña as fast as a year. That's where the idea of climate whiplash comes from. Wet years followed by dry years, floods followed by droughts, heat waves stacked on top of already warm conditions. ENSO is shifting the odds, but the stakes attached to those odds are also rising. And this is where a misconception needs clearing up. ENSO is not causing climate change. ENSO is not changing anything about greenhouse warming. It's not an excuse to dismiss long-term trends. A weak El Niño or a strong La Niña is not an excuse to say that humans are not affecting the climate. You can often hear people say, well, that's just an El Niño, or that's just a La Niña, as if it explains everything. It doesn't. ENSO explains the timing. Climate change explains the severity and the direction. ENSO tells us when and where extremes are likely. Climate change stacks the deck and determines how intense and extreme they can become once they happen. They're not competing explanations. They're layered on top of each other in sometimes complex ways. And that complexity is a concern, because a climate system that swings naturally becomes more dangerous when it's operating in overdrive, not because anything here is new, but because the margins for recovery are smaller. And that's the takeaway I hope you get here. ENSO isn't broken. It's not really changed that much. It's being stressed, and it's reacting to that stress. ENSO reminds us that the Earth isn't a collection of separate parts. It's a single, interconnected system. Heat stored in the Pacific doesn't stay in the Pacific. It eventually reshapes winds, storms, ecosystems, and daily life far from the ocean. Understanding ENSO doesn't help us control the weather, but it does give us something just as important, a context. It helps us to see the difference between short-term swings and long-term change, between natural rhythms and the added strain of a warming world. As climate change raises the background temperature of our planet, scientists are focused on the data. ENSO's natural heartbeat is growing louder, and learning to listen to it carefully is one of the best tools we have for preparing rather than reacting. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate that you've been too afraid to ask, or if you have a differing opinion, please let me hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.